Good afternoon. Thank you for taking the time to join today's webinar, Control Valves and Valve Flow Testing. The NEL webinars are sponsored by the UK Government's Department for Business, Energy and Industrial Strategy, or BEIS. A recorded version of this webinar will be available to you along with a slide deck after today's webinar. We'd love to hear from you, so please submit your questions at any time during the webinar. You'll find the Q&A panel on the left-hand side of your screen underneath the video feed. Your questions won't be seen by any of the other attendees, and we'll do our best to answer as many questions as we can, but if we do run out of time, we will follow up any unanswered questions. My name's John Dodds. I'm a bid manager here at TÜV SÜD. I've been with the National Engineering Laboratory for over 19 years, and in that time I've been involved in many valve projects. Much of that work has been done with today's presenter as well. Today we're going to be discussing control valves and valve flow testing, and I'm pleased to introduce your presenter today, Tariq Buswara. Tariq's a project engineer with the TÜV SÜD National Engineering Laboratory. Tariq is the technical lead for wet and dry gas calibration services and valve testing here at NEL. He's one of the lead developers working on NEL's new data acquisition, uncertainty and calculation software as well. So I think if you're ready, Tariq, I think I'll hand over to you now.
Okay, thanks very much, John, and good afternoon, everybody. I'd just like to welcome you again to today's webinar, the topic of which is control valves and valve flow testing. So I'll just give you a quick rundown of the contents of the webinar. I'll start off with a little bit about control valves, what we mean by a control valve, some of the different types and styles, and some of the things that you need to consider when selecting a control valve for a specific application. The bulk of the presentation is going to be on control valve flow testing and how we validate parameters such as the flow coefficient and pressure recovery factor of valves. But before that, there are some sort of key technical concepts and definitions that are important not only for just general valve operation, but they're quite critical when it comes to flow testing valves. And I'll finish up with a little bit on control valve wear mechanisms. So some of the things like erosion and corrosion that can affect a valve's performance over time. And finally, how CFD modelling or computational fluid dynamics can be used as a tool to sort of manage that wear. So I'll start off with talking a little bit about control valves, types and characteristics. Although isolation valves and non-return valves are technically control valves, they're not the main focus of this presentation. Isolation valves generally operate in two modes, either fully open or fully closed, and non-return valves generally have a primary purpose where they only allow flow to move in one direction. But when I say control valves, what I really mean are pressure or flow control valves, and these valves regulate or control the rate of flow of a fluid by varying the size of the flow passage. So control valves generally, as flow goes through them, they restrict the flow. As the flow is restricted due to Bernoulli's principle, the velocity increases and the pressure decreases. So that's how they essentially control the flow of the fluid. Control valves come in all different types and styles. If you work in the oil and gas industry, choke valves are quite a common type of valve used there. Again, they can have different subtypes. Quite a common style is the cage and plug type. So you have an internal cage that has sort of holes bored throughout the circumference. That sits inside the valve, and you have a central plug that moves up and down the cage, and that obviously varies the size of the flow passage. Some of the pictures here are, again, different types of valve. So we have a ball valve. That's where you have a cylindrical or sphere, with a cylinder bored through it. As you change the sort of angle of the ball, that exposes the cylinder to more of the flow. Butterfly valves, you have a central disc. You vary the angle of the disc. Again, that changes the size of the flow passage. The cross section here is actually a globe valve. And again, you've got a plug that moves up and down. And again, that changes the available flow area. So there's more than can be listed here, but essentially they all do the same thing. They're varying the size of the flow passage. Now, depending on the design of the valve, it will have a different opening characteristic. So what do I mean by this? Well, you might have an application where you require quite a fast response. So as soon as you open the valve, you get quite a large increase in flow capacity. So in that case, you might decide to go for a fast opening type of valve, such as a globe valve. On the other hand, you might want more finer control just as you're opening the valve in its lower stages of travel, with a more rapid increase as the valve moves towards 100% open. So you might go for an equal percentage opening characteristic. On the other hand, you might just want a linear response where you open the valve 50% and you get a 50% increase in flow capacity. So there are different opening styles depending on the design that you choose, and it really depends on your sort of personal requirements. Do you require a fast response, or do you want sort of finer control in the early stages of valve travel? Another quite important aspect of control valves is the actuation. This is quite a big topic, so I'm not really going to cover it in much detail, but actuators can come in all different shapes, sizes and types. The simplest being manual operation, so either a hand wheel or a lever, which allows you to move the valve or change its position. Power actuation, so it could be electrically actuated, or it could be a pneumatic actuator that's powered by compressed air. Or the valve could be fully process or self-activated. So a good example of that is actually check valves. They have what's known as a cracking pressure. So that's a minimum differential pressure. And once that is reached, the valve will actually open and allow flow to go through. And that's completely sort of process actuated. There's no external actuation or force required for that. Typically, you'll have a combination. So you'll have a manual sort of actuation or override, and you'll have power actuation as well. Critical things are obviously what's the torque required to operate the valve. That again is going to vary depending on the flow going through the valve, what type of fluid that you're using. The failure mode is also quite important. So what happens, say if you've got power actuation and there's a loss of power, a loss of compressed air, does the valve fail in position, or does it fail fully open or fully closed? Again, it depends on the type of application you're using it for. At NEL, some of our valves in our facilities, they'll fail closed, because if they don't, it could lead to a loss of containment of our fluid. In other instances, they'll fail open because it might lead to a sort of dangerous buildup of pressure. So depends on the specific duty that's required for the actuator. So when it comes to control valve selection, there are several things that you need to consider when selecting a valve for a particular duty. I've just listed a few of the main ones here. There are more that can be listed here, but I'll go through some of these in a little bit of detail. So flow range is important. So what kind of flow rates are you expecting to control via the valve? A critical parameter for that is the flow coefficient of the valve, which I'm going to talk about later in the webinar, which is kind of a measure of the efficiency of the valve of allowing flow. But the flow range is going to dictate what type and size of valve that you choose. Temperature and pressure is obviously quite critical. Temperature of your process fluid can dictate things like the materials of the valve. So for example, if it's ambient temperature, then carbon steel might be suitable, but if it's for cryogenic conditions, you might have to look at things like stainless steel. Pressure, you need to make sure the valve body is suitably rated for the operating pressure. So it needs to be a suitable thickness to contain the pressure. You need to have flanges if the valve is flanged that are rated appropriately as well. The fluid properties are important, so certain things like sealing materials within the valve will be compatible with, say, water, but may degrade with certain fluids such as oil or crude oil. Fire resistance, what's the kind of environment the valve's going to be installed in? Does it have to have a certain level of fire resistance? If the valve is going to be used as an isolation valve as well as a sort of control valve, what's the allowable leakage? So valves will have a specific sort of leakage class. So when they're used in their fully closed state, there will be an allowable sort of leakage level. And depending on the fluid and depending on your application, a certain amount of leakage might be acceptable. In other cases, you might have to have a higher class in terms of the leakage class. Noise limitations. So this is quite an important one. Control valves can be very noisy, especially if cavitation is likely to be a problem within the valve, which I'll talk about later on. But you might have, obviously, noise regulations that you need to comply with, or the valve might be intended for, let's say, sensitive applications where noise might alert people to certain things. In that instance, noise becomes quite an important factor when selecting the valve. Piping, where's the valve going to be installed? You don't want to install a valve that's, more than half the size of the pipeline. Again, the pipeline will have a certain connection type that will dictate what the connection type you choose on the valve. And materials. So if the valve is going to be used in an erosive environment, you might want to select erosion-resistant materials. If corrosion is likely to be an issue, you might select materials that are resistant to corrosion as well. So that's just a kind of brief overview of some of the things that can influence valve selection. Although it can seem a little bit overwhelming, the good thing is valve manufacturers or suppliers, it is really their responsibility to supply something that will meet your duty. So as long as you're, describe your process in a lot of detail, it's really up to them to, supply something that will meet that duty. But it's always good if you're an end user of a valve or you're selecting a valve, that you have an awareness of all these type of things, because it can allow you to make a more sort of informed choice when selecting a valve for use. So that was just a kind of brief overview or introduction to control valves. I'm now going to talk about some key technical concepts and definitions. These are important not only for general operation of control valves, but they tie in obviously with flow testing of control valves. So they're quite important in that aspect as well. So the first term that's quite important is the flow coefficient. This is a fairly ubiquitous term when talking about control valves. So if you've ever bought a valve or looked at a valve data sheet or catalogue, you'll have seen this term stated. And this expresses the performance capability of a control valve. So in simple terms, it's really a measure of how efficient the valve is at allowing flow. In more practical terms, it's the US gallons per minute that will result in a pressure drop of 1 psi across the valve. This is with water at a temperature of 60 degrees Fahrenheit. So you'll often see CV quoted without any units, which can lead some people to believe it's actually a unitless term, but it does in fact have units. It's calculated using this formula. So size or type, so of industry standard for comparing valves. So if you're ever selecting a valve for use, generally you need to calculate a required CV, which will then let you select a suitably sized valve. Choked flow, so this is in a liquid system. When we talk about choked flow, is where you have vapor formation within the valve. So the pressure has dropped below the vapor pressure of the fluid, and the vapor formation is so large that you can't get any further increases in flow rate through the valve. So the vapour starts to form, and it forms to such a level that it prevents any further increases in flow rate. And that kind of leads us on to cavitation and flashing. So cavitation is a flow phenomenon where you're flowing through the valve. So the valve has an inlet pressure. As it flows through the valve restricts the flow. The pressure starts to drop. It eventually reaches a point in the valve which is known as the vena contracta. This is the point of lowest pressure or maximum sort of restriction within the valve. Once it passes that point and it starts to exit the valve, the pressure will then recover, and then you get this overall pressure drop across the valve. Now, if your inlet pressure is not sufficiently high, you can drop below the vapour pressure of the fluid. So vapour bubbles start to form. And if the recovery takes it back above the vapour pressure, the bubbles that have formed start to implode and collapse. And that's what's known as cavitation. Flashing is similar, where the pressure drops below the vapour pressure, but the recovery is not sufficient, and what you get is this mix of vapour and liquid that travels downstream of the valve. So both of these are generally undesirable. You want to avoid them for control valves. Cavitation can result in significant noise emission, so this sort of action of implosion of the vapour bubbles results in serious noise. It can lead to serious vibration of the valve. So if there are moving parts in the valve over time, it's going to damage them. And it can lead to erosion, so material loss due to collapsing bubbles and shock waves. So it can damage the valve over time. Flashing, in a similar manner, will result in significant noise emission. You get vibration of not only the valve, but the entire pipeline due to the imbalance between liquid and vapour phases. And you can also get erosion or material loss due to liquid droplet impact. So generally, these are bad for the valve and you want to avoid them if possible. And this leads us on to the pressure recovery factor. So the pressure recovery factor is a measure of the capability of the valve to transform kinetic energy of the fluid at the vena contracta into pressure energy. In simple terms, it's how well the valve recovers pressure once it hits the vena contracta, or the point of maximum restriction. It can be calculated using this formula, which is based on choked conditions within the valve. So Qmax is the choke flow rate, C is the flow coefficient, P1 is the inlet pressure, PV is the vapour pressure, and the other terms are either unit conversions or fluid-specific properties. The thing to remember with the pressure recovery factor is the higher the number, the worse the valve is at recovering pressure. So these are some typical values for different valve types. Ball valves generally have much better pressure recovery than a globe valve, for example. However, that does mean they are more susceptible to cavitation. So generally, a lower FL number means the valve is more susceptible to cavitation. And the FL number can be used to predict safe operating limits for the valve, which I will talk about near the end of the presentation. Another term is the cavitation index, or sigma. This is a measure of the intensity of the cavitation within the valve. It can be calculated using the inlet pressure P1 minus the vapour pressure divided by the overall pressure drop. This is quite a useful chart in understanding what sigma means. So on the y-axis, we've got acceleration on the valve body. You can just think of that in terms of the intensity of the cavitation. And you've got sigma on the bottom, and you actually read it from right to left, because a lower sigma indicates a more intense level of cavitation. So you start off with incipient cavitation, which is where you've got small bubbles that form within the flow stream. Moves up to constant cavitation, where you get mild, steady popping or cracking. right up to choking cavitation damage. So this is where the cavitation is fully developed and the flow rate can no longer increase with an increase in differential pressure. So eventually cavitation reaches a point where it chokes the flow and you get no further sort of flow increases through the valve. Now, if you've ever bought a valve or a control valve, a lot of the time the manufacturer will provide some guidance in terms of sigma levels. So you might have a table such as this. This is just for a typical globe valve. And what it allows you to do is, for your operating conditions, calculate a sigma, and then that tells you if cavitation is going to be an issue with this valve. So if you've got a high sigma, or in this case, then the cavitation is less likely, so if it's above 2. As sigma drops, the potential for more severe cavitation increases. So if you calculate a sigma and it's 1.1, in this instance this valve is probably not suitable, or you might have to take steps to control the cavitation, maybe increase the inlet pressure, or select a different valve if it's not suitable for your particular application. So those were just some key kind of concepts that are important not only just for general operation of control valves, but they will be quite important for flow testing. Before I move on to flow testing, I thought I'd just give a little simple example to show how CV, or flow coefficients, can be used in practice. So the example we've got here is a water tank that has a variable water height of 5 to 40 meters. It has a port on the bottom that's open to atmosphere, and there is a control valve on that port. And the task is to determine the size of the control valve to regulate the flow of water from this tank. So the water is just draining by gravity. You have a water height between 5 and 40 meters, and you want to achieve a flow rate of 100 liters a second. So really what you need to determine is what CV range does this valve have to cover. Well, we can take the CV formula. For the purposes of this example, I've simplified the specific gravity to 1 because it's water. In reality, even with water, the specific gravity varies with temperature and pressure, but for this example, 1 is fine. So we need to determine a CV range. So the maximum CV is going to occur at the minimum height of water. So if you think of CV, for a given flow rate, a higher CV results in a lower pressure drop. So the high CV is going to occur at the lowest pressure drop. So the lowest pressure drop is basically the 5 meters of water acting on this valve. So we need to convert 5 meters of water to differential pressure in PSI, and we need to convert 100 liters a second to US gallons per minute because that's the units that the CV formula expects. You put those numbers in and you come up with a CV of 597. Again, the minimum CV occurs at the maximum pressure drop, and that's going to be when you have 40 meters of water acting on the valve. And you put the numbers in the formula and it gives you a CV of 211. So for your duty, or to achieve 100 liters a second, you need a valve that can cover a CV range of 211 to 597. So what would be your next step? Well, you might go to a valve datasheet or catalogue. This is just a typical example for a butterfly valve. And you can see that the 6-inch size can comfortably cover the duty. Generally, you want to avoid using a valve at its extremes in terms of its opening positions. So you want to avoid using it in its sort of lower 10% and upper 20% because it's generally harder to control the flow. You'll also notice that it provides FL data as well. So the next section is going to be on valve flow testing and how we actually calculate these numbers. So where does the CV and where does the FL number come from? Which brings us on to flow testing. As John said at the start, it's something that NAL's got quite a lot of experience in. We've worked with valve suppliers, valve designers and several different end users that have came to us who they want to validate the performance of their control valve. So some of you might ask, well, why bother testing or flow testing a valve? If I've got data from the manufacturer, do I really need to use a flow test? The first thing it does is it provides confidence. So if you independently verify that a valve CV is correct, it gives you confidence that when the valve is installed, it's going to meet its intended duty. We've tested a lot of valves that are intended for maybe offshore service or even subsea service. So once the valve is installed, it's going to be very difficult to rectify any problems with the valve. So testing it before it's deployed can give you confidence, and it can actually save you a lot of money in the long run. It can validate predicted data. So, for example, we've done tests for valve designers or manufacturers. They've maybe got a prototype. They want to test it before it goes into production. So if you test it, you can iron out any issues with the valve before it's deployed. And if you do an independent test, it can bring up these issues early on. So we've tested valves where, yep, the predicted data has matched the test data, but we've had instances where there's been quite a difference. Done early on, the user could either change the valve or they could adjust their process conditions accordingly to suit the new characteristic. And it's also quite important for predicting safe operating limits. So this is where we test for the pressure recovery factor, which can be used to check if you're at risk of choking the flow or if you're at risk of developing cavitation. So there are two kind of main test standards when it comes to establishing the flow coefficient and pressure recovery factor of control valves. The main one is the ISA 7502 control valve capacity test procedures. But these both essentially describe the exact same test procedure. So NEL tests in general accordance with both those standards. So if you decide to obviously flow test your valve, you need a flow facility. This is actually an image of NEL's flow facility. We've got a globe valve that was actually undergoing a CV test. The good thing about NEL's water facility is we're the custodians of the flow measurement standard for the United Kingdom. So all the instrumentation, all the flow measurement equipment is fully traceable and has a low uncertainty. So the first thing you need is a flow test facility that can obviously accommodate the valve depending on its size. Once you've found a facility, you then need to set up the tests that need to be considered when flow testing a valve. So the valve's got to be installed between pipework. So the upstream and downstream pipework is quite critical. You don't want to install pipework that has a massively different internal bore versus the valve's bore. You want a nice match between the valve and the pipework because that will give you a smooth flow profile going into the valve. If you have big steps in the bore, it can result in a larger pressure drop than you would normally attribute just to the valve. To calculate a CV, you need two things. You need to measure the flow rate and you also need to measure the pressure drop across the valve. So you need some way of actually measuring the pressure. So you need to install pressure tappings on the pipe. The pressure tapping dimensions are quite critical. The standard actually has guidelines in terms of the size of the tapping, but generally, as a rule of thumb, you want to make the through hole in the pipe as small as possible, and you want to make sure it's a sharp hole. If you just go ahead and bore a big sort of branch into the pipe, the pressure measurement's not going to be accurate. One thing that is important is the distance of the pressure tappings from the valve. So the standard dictates 2 diameters upstream and 6 diameters downstream. The reason for that is to account for pressure recovery. So if you think back to the cavitation graph, the flow goes through the valve, it hits the vena contracta, and then it recovers. Now, you don't want to measure the valve while it's still in its recovery phase or the flow's in its recovery phase, because that could give you a pressure drop that's actually larger than the overall pressure loss. So the distance is quite important, not only for valves, but anything that you would be measuring the pressure drop across. You want to account for pressure recovery. Stem calibration is critical. So before you obviously start the test, you want to make sure that if you establish the CV at a valve opening position, you can reproduce that position when you use the valve in practice. So you don't want to establish a CV at 50% and then in the field you think the valve is open 50%, but it's actually only 45% open. So you want to make sure the stem or the valve travel has been properly calibrated. You need a differential pressure measurement device. So we have very high accuracy pressure transducers that we use to do that. And you need to measure the flow rate. So you need to measure the volumetric flow rate. We have obviously flow meters that are calibrated to a very low uncertainty for that purpose. One of the things that you need to consider when doing a CV test is the flow needs to be turbulent through the valve. So the general aim is to try and achieve a Reynolds number of greater than 100,000 within the pipe. Sometimes that's not always possible due to you might have a particularly large valve, but generally you want to make sure that the flow is at least turbulent through the valve trim or the internal surfaces of the valve. So once you've set up your valve properly, you then want to commence the flow test and establish the CV. So the way we do it at NAL, we set up flow points for each valve opening position covering 3 different differential pressures. And the reason we do 3 different differential pressures is for each of these differential pressures, if you calculate a CV, it should roughly be the same. So each differential pressure should have the same CV if you measure the differential pressure and the flow rate. If one of these points deviates from the average, it kind of indicates that you might have cavitation within the pipe. In that instance, you can increase the inlet pressure. So you want to try and have as high an inlet pressure as possible to suppress cavitation. And then basically you calculate a CV for each data point and average the 3, and that gives you the CV for that opening position. So if it's a valve that has a number of different opening positions, we would do that for each position, and we can build up a chart of the CV characteristic of the valve. So this is an example. This was I think it was a choke valve that we tested, and the light blue is the NAL test data. The dark blue was the predicted data from the manufacturer. And in this case, there was quite good agreement. So this gave the end user confidence that the valve was going to meet its duty properly. On the other hand, you might have a situation where the test data does not agree with the predicted data. So this was a good example. This was another choke valve, and at fully open, the valve had a 20% deviation. So the CV, they thought it was going to be 82, and it was actually around 65. Now, if you think about CV, that for a given flow rate, a higher CV is going to result in a lower pressure drop. So they were expecting a lower pressure drop through this valve, when in reality, the CV was, 20% different. The good thing was, this was before the valve was installed. So rather than find this out after it's been installed and commissioned, they could take steps to either change out the valve internals or adjust the process conditions accordingly to accommodate for the new characteristic. The next parameter that we want to establish is the pressure recovery factor. So this is the sort of term that can be used to predict if you've got choked conditions within the valve. So how do we actually establish the FL number? Well, first off, we take a data point with a very high inlet pressure and a low differential pressure. So this is essentially a point under sort of normal flow conditions. We calculate a CV and we make sure it matches the CV that we've determined earlier. So generally you do a CV test, then an FL test. We then want to take a data point with the outlet pressure in the facility reduced to a minimum. So what do I mean by this? We're trying to induce as much cavitation as possible. So this is one of the rare instances where we actually want to induce cavitation. We're trying to choke the flow as much as possible. And then once we have these two extremes, we can plot data points in between both conditions. And once you've done that, you can produce a chart that looks like this. So on the bottom, we have the differential pressure across the valve. On the left axis, we've got the flow rate squared, and on the right, we have the calculated FL number. So under non-cavitating or non-choked conditions, the differential pressure versus the flow rate squared should relationship. So you can see the initial points are lying on this straight line, but they start to bend away from the line. So that bending away is cavitation forming, it's vapor forming within the valve. And what we need to do is determine when they start to deviate from this straight line. So we've got our normal flow point, we've got our extreme, that's as much cavitation as we can realistically generate within the facility. And they start to deviate from the straight line roughly at this point. We've also got the FL data plotted on the top in orange, so we can fit a line through that, determine where it crosses, and that gives us our FL number. So I've called this the FLA number, not the FL number. The reason for that is it's the point at which cavitation is just starting to make itself evident hydrodynamically. So what does that mean? It basically means when do those points start to deviate from a straight line? It's not the maximum FL value. So a lot of the time in valve literature or data sheets, you'll see an FL value quoted. That's actually when the valve is fully choked. The FLA number is slightly before that, but it's a point at which you've got high noise levels and significant cavitation erosion. So it's a point at which you don't want to operate the valve at. And it lies between the constant cavitation sigma level and the choking cavitation level. So if I show you the sigma chart again, it's somewhere within this region. Incipient cavitation may still occur before this point. The thing about incipient cavitation is it's so sort of low level that you can't really detect it just through measuring differential pressure and flow rate. You need specialist noise measurement equipment to detect the very onset of cavitation. They tell you to see basically significant cavitation damage. So, if you've established the FL number experimentally, what can you then do with that number to predict safe operating limits for your valve? So you can use this formula. The delta P is the choked or cavitating pressure drop. FL is your pressure recovery factor that you've just established. P1 is your valve inlet pressure. FF is just a term that's specific to the fluid. It's based on the vapor pressure and the critical pressure, which can be looked up for things like water. And PV is the vapor pressure of the fluid. So I'll just go through a quick example. In this case, the valve, or your valve, has an inlet pressure of 140 bar. You're running with water at 20 degrees C, and your pressure recovery factor for the valve at this position is 0.9. Now you require to drop the pressure by 120 bar. So you want to know, if I drop the pressure by 120 bar, am I going to choke the flow? Am I going to start to form vapor within the valve? Is cavitation going to be an issue? So if we take the formula and we plug in the data, we get a choke 15.4 bar. So choked flow is going to occur at 113.4 bar for this inlet condition, but you require a DP or a delta P of 120 bar, which is greater than 113.4 bar. So If you drop the pressure by 120 with this inlet pressure, you are definitely going to see cavitation. So it wouldn't be recommended to operate the valve at this condition. And the important thing to remember is without the FL number, or without confidence in the FL number, it's very difficult to actually determine if you're operating at a safe level. So that's valve flow testing. I'm now just going to talk a little bit about control valve wear. So what are some of the things that can degrade and affect the performance of control valves over time? These are some of the main wear mechanisms that will affect a control valve's performance. I'm going to talk about some of these in a bit more detail. So the first one is corrosion or corrosive wear. It is, by and large, the most common cause of wear in valves. So this is where the surfaces of the valve interact with the environment, and that results in corrosion. It can increase the surface roughness, not only in the outer surface, but the internal surface of the valve as well. If the surface roughness increases, it can reduce the CV of the valve. So if you think of a valve in its brand new state, after it's corroded, the characteristic may change, the pressure drop may increase, and that can cause issues as well. Corrosion can also result in parts seizing, so it makes the valve difficult to actuate or operate, and in more serious cases it can lead to a loss of containment of the fluid. Abrasive wear is where sand or other particles can get stuck in between surfaces. For example, gate valve sliding surfaces or ball valve rotating surfaces. The image here is an example of a ball from a ball valve, and sand has actually scoured the outside of the ball, and over time that's going to remove material and affect the performance and the sealing capability of the valve. And these are some images here where abrasion has caused the valve to essentially leak over time, so the valve no longer seals. It's no longer going to properly contain the fluid. Particulate wear is another common cause of wear in not only valves but other components. And this is erosion due to solid particles such as sand impinging on surfaces at high velocity. The key thing for this is it's an exponential relationship with velocity. So it's roughly a function of velocity to the power of 2.6. So small increases in flow velocity or particle velocity give you large increases in erosive wear. And this is a sort of dramatic example of particulate wear. So this is the internal cage from a control valve, and you can see that erosion has essentially eaten away at the cage. So, that valve's no longer going to perform as intended. You might set that valve in a particular position, but because there's been so much material loss, the CV characteristic again is going to change as well. This is another example of wear on a choke plug. So the plug that moves up and down in the choke, particles as they move through the valve have gouged sort of a groove within the plug. Over time that's just going to get worse, and eventually it's going to cause significant performance degradation within the valve. Cavitation erosion is another wear mechanism. So we've talked about cavitation. That's where vapour forms within the valve, and as pressure recovers, the vapour bubbles implode, and the collapse of these bubbles can remove material. The image here isn't actually a valve, it's a multi-orifice plate, but it's an example of cavitation erosion has started to remove material from this object. So those are some of the things that can degrade a valve's performance over time. So the big question is, well, how do you actually prevent this wear? How do you stop it from happening? If it's a particulate wear, for example, the biggest thing you can do is velocity reduction. So if you can reduce the velocity, then that can have a massive impact on particulate wear. Material selection is critical. So if corrosion is going to be an issue, you can select corrosion resistant materials, or if erosion is going to be a problem, there are things like tungsten carbide that will provide much better erosion resistance over, say, things like steel. However, it is much more brittle than regular steels, for example, so that's another thing you need to consider. If cavitation is likely to be a problem, you can opt for designs that are known as multi-stage valves. So the working principle of these is, instead of dropping the pressure in one large sort of chunk, the valve has different stages where it drops the pressure in smaller increments. The advantage of that is you avoid dropping below the vapor pressure of the fluid, so you don't form vapor, and as a result you avoid cavitation. However, a lot of the time, wear is just something that you maybe have to live with. You know that the valve is going to be installed in an erosive environment, for example, and it becomes a case of managing the wear, so predicting the life cycle of components and planning shutdowns and changeouts. And that's where CFD can come in, and it's quite a sort of powerful tool for predicting the degradation of valves. And once you combine it with physical testing, it can become an even better tool for predicting the life cycle of components. So that's what I'm going to talk about just to finish up the webinar. So what is CFD modelling, or computational fluid dynamics? To put it simply, it's simulating the behaviour of fluid flows using numerical models. And you can then visualise the behaviour of the fluid flow in various different ways. So how would you actually set up a CFD model? Well, first off, you would define your geometry. In this case, we have a non-return valve, which is of the flapper design. So you define the geometry. You then divide the fluid zone, so the zone at which the fluid will exist in. You split it up into discrete cells called the mesh. You set your input or your boundary conditions, and then the CFD code will iteratively solve the Navier-Stokes flow equations in each discrete cell. So it's obviously a bit more complicated than that, but that's the general way in which a CFD model is put together. And once you've actually simulated the behaviour of the flow, you can then inject particles such as sand, and you can model the trajectory of the particles and the effect that can have on the material loss within the valve. So this is an example of something that you can produce with CFD. So this is the same check valve, and this is a contour map of material loss within the valve. So areas in red are areas of high erosion, and areas in blue are areas where the erosion is not as significant. So it tells you problematic areas with the valve. So this tells you that the flapper within this check valve is going to erode faster than the body, which makes sense because that's where the majority of the particles would probably hit. But it's very good at visualizing where erosion is going to occur. This was another example. The customer wanted to determine if flashing would occur within the valve. Now the advantage of CFD here was the valve itself was too large to test experimentally. The operating pressures were far beyond what a flow lab could achieve. So CFD was very good, and it allowed you to predict, is flashing going to occur for a given set of inlet conditions. And you could also visualize things like the velocity of the flow and the path of the flow lines as it moves through the valve. Now CFD, especially when it comes to erosion, is very good at identifying areas of erosion or hotspots of erosion, but it can sometimes be slightly off, let's say, when it comes to the magnitude of the erosion. So how much material is actually being lost over time. And that's where you can combine it with a physical test to back up and validate your model. And you can do that in a rig such as this, which is a 3D model of NAL's erosive flow loop. It's a very simple loop. It just allows you to circulate sand and water through different components, such as control valves. You can subject them to sort of accelerated erosion, measure or quantify that erosion, and then use that physical test data to inform a CFD model. So an example here is erosion in a choke valve cage. So on the right, we have the physical test specimen. So you can see that it's been badly eroded by sand. And on the left, we have the CFD model or the CFD visualization. So we can take the physical test specimen and determine the erosion before and after, and use that data to tweak the CFD model, maybe adjust the properties of the material. And once you've got confidence in the model, you can then apply it to different scenarios, or perhaps you've flow tested maybe a smaller prototype, and then you want to apply it to something much larger. If you validate the model first with a smaller device, you can then apply it to maybe bigger devices, or maybe flow conditions that maybe weren't possible to test in the laboratory. So, once you combine these two tools, it can become quite a powerful sort of management tool for valves, especially if you know they're going to degrade over time. What you really want to do is estimate their effective usable life, so you can plan out shutdowns and changeouts for the component. So that's basically the end of the webinar. I'll just kind of briefly go through what we've covered. Started off talking about control valves. What is a control valve, some of the different types and styles, and what are some of the selection criteria that you should consider when choosing a control valve for use. Went over some key technical concepts and definitions like flow coefficients, pressure recovery factors, cavitation, flashing, and choked flow. Talked about flow testing of control valves. Why do we flow test control valves? To validate their performance. How you effectively set up a control valve flow test. What are some of the things that you need to consider? We then talked about some of the wear mechanisms that can affect and degrade control valves over time, and there were some images that had examples of that, and obviously how CFD modelling can be used as a tool to sort of manage and predict things like erosion in the field. So yeah, that's the end of the webinar. Thanks everybody for tuning in. If you've got any questions, please send them in. Happy to answer them. And if you think of anything after the webinar, obviously get in touch as well. And I think I'll just pass you back to John to finish up.
Thanks, Tarek. That was good. Okay, we've got a few questions. Let's run through some of them now. What is the KV coefficient, and how does that differ from CV? And is the test procedure the same? This is actually something that comes up quite a lot, because I do get quite a lot of customers asking me for a KV test as opposed to a CV test. So what is the difference, Tarek?
So KV is essentially the same as CV, it's just different units. So CV was the flow rate in US gallons per minute that results in a pressure drop of 1 psi. KV is the flow rate in meters cubed per hour that results in a 1 bar pressure drop. So it really is just a different set of units. You'll find that KV is maybe more common in Europe, whereas CV is more common in America. But the flow test procedure is exactly the same. Obviously, you just need to be mindful when you're calculating KV that you've got the units in the equation correct. There is an additional thing that's our K, which is a loss coefficient. That is slightly different. Again, the test procedure is similar. There are test procedures for loss coefficients where you install the valve, flow test it, and then you remove the valve, and just test it without the valve in the pipeline. But when it comes to control valves, generally CV is the most common, but KV is essentially the same thing. It's just a different set of units.
Okay. So basically, it's the same, only different. Yeah. Okay.
Yep.
How do you quantify erosion or erosion rate during an experimental test?
So there's a number of different ways you can do it. The simplest is a visual inspection. So inspect the device before it is subjected to erosion, then remove it and visually inspect it, and you can see the wear path of the particles. Weight loss measurement is quite important. So weigh the component before erosion, weigh it after. You can determine the weight loss over time. If you can get access to the internal surfaces, you can do dimensional measurement. So in the past, we've sent things away to be dimensionally measured with very high accuracy. One thing we actually did was, for a particular project, we sent the component away to be digitally scanned. So it was a high resolution mesh scan was developed of the model in its basically uneroded state. We then subjected it to erosion, rescanned it, and then you can overlay the two 3D meshes on top of each other, and that produces a really sort of high accuracy map of erosion. You can obviously manipulate it and click on anywhere on the object, and it tells you exactly how much material has been lost. And so that is probably one of the better methods, but it depends if you can get access to the component. So things like a bit of pipe, you can't get access to the internal surface unless you slice it in half. So it's quite difficult to do that. So that's where we might do weight loss or visual inspection once we've subjected it to erosion. So.
Okay. All right, next one. What are some of the ways you can monitor erosion, corrosion in the field?
So there are erosion or corrosion probes that you can install. So say you've got a component that you're worried about. There are these probes that you can install in the pipe, say, and the way they work is it's the electrical properties of the probe varies as it erodes or corrodes. So for example, erosion probes, the resistance of the probe changes as it erodes, and that can be used to give you an estimate of the erosion rate. You can use ultrasonic thickness measurement. So obviously a lot of the time you can't get access to inside the pipe, which is where the erosion is happening or the corrosion. You can either use a device which allows you to determine the thickness of the pipe wall. You do get things now where it's like an ultrasonic blanket almost. You can strap it around the pipe, and that can give you continuous sort of monitoring of erosion, continuous monitoring of the wall thickness within the pipe. So over time, it'll alert you to the fact that your wall thickness might be reaching a sort of dangerous level. One thing we have done, we test a lot of material coupons, and sometimes people will install little material coupons as sort of sacrificial items that can be removed and periodically checked to determine how much material is actually being lost. And if you can get access to the device, visual inspection's quite good. And if it's control valves, over time, if there is going to be erosion, if you can instrument the valve, say monitor the differential pressure across it, the CV characteristic of the valve will change over time. So if you can actually track that, then again, that can be an indication. If the valve isn't performing as expected, that could indicate that something has happened, e.g. The internal surfaces have started to erode or corrode. So there are a few different things that can be done to sort of track erosion in the field.
Okay. Right. Well, I think we're just about out of time. As I mentioned earlier, if we haven't managed to answer your question, don't worry. We will follow up and respond to you after this webinar. You will receive a link to the recording for today's presentation. Get in touch with us and let us know if there's any webinar subjects that you'd like us to cover in future. It's great to hear exactly what you're interested in, so please let us know. You can get in touch with Tariq or I directly, or send any queries to info.uk@tuvsud.com, or visit our website tuvsud.com/UK. And on behalf of myself and Tariq, thanks for joining us, and enjoy the rest of your day.